So good evening, everyone. Thank you for joining us today. We are very proud and happy today to have here the presence of Professor David Gamez, who will talk today with us about natural and artificial intelligence, natural and artificial consciousness. This is a very old theme in AI, which is an open problem, very enticing, difficult, and it's very good to have him to talk to us today about this topic. This talk is part of the collaboration and partnership of the University of Campinas, the Institute of Computing here, and the Pontifical Catholic University in Rio de Janeiro, PUC-Rio. In the collaboration that we called kindly Connection Rio Campinas, or in Portuguese, Conexão Rio Campinas. This talk is part of this series, and it's also organized by the Artificial Intelligence Lab, Recode AI, here at the Institute of Computing. Professor David accepted the invitation to talk to us today, and he's a senior lecturer in computer science at Middlesex University, UK, with expertise in philosophy, artificial intelligence, and psychology, which is a very nice complement of areas. In previous research, he has worked on agent systems, spiking neural networks, and the philosophy and science of consciousness. His current project is a new universal measure of intelligence based on prediction. He has a website, so I invite you to access the website later. His most recent book is Human and Machine Consciousness, which came out in 2018. And also I put the link here for you to take a look later. So in the name of this partnership, David, thank you very much for accepting the invitation. The stage is all yours. I will unshare my screen now. Please go ahead and share yours.
Okay, great. So let me just share and then so we sort of tested this. So if anyone has real issues with the resolution, then just let me know and we'll work something out. I can maybe share half or something. That's what I do usually when I'm teaching. All right. Okay. So lovely to be invited. Really appreciate it. Alison and Marcus. I'm really tired. I'll share that now. I've had a long day. So I'll do my best to sort of speak at a normal pace and be coherent. But if I go too fast, then just let me know, yeah, because I've sort of prepared kind of an hour's talk at my usual pace, and I've sort of been made aware that maybe my usual pace is a little fast. So I'll try and go more slowly, which means it might go slightly longer, and I'll do my best, yeah. But do stop me, And there's a couple of points I'm going to pause for kind of questions. It might be better waiting for those, but if you've got some burning stuff, I don't mind sort of taking up some of the question time, stopping to clarify some points or something. Yeah, it's informal, right? I mean, I don't mind. Okay, so I'm Middlesex University, London, UK. Yeah, I guess we had a very good introduction, so I need to get into that. So this is what I'm going to talk about. So it's kind of a talk of three parts, really. Yeah. So the first part of the talk is going to be kind of covering the work I've been doing in the last couple of years on intelligence. I've sort of developed this new sort of way of looking at intelligence and its relationship to prediction. And in tandem with that, I developed a sort of new algorithm for measuring predictive intelligence. I'm going to run through all that. And then I'm going to go sort of through the sort of consciousness kind of stuff. And then, so, trying to sort of look at the, some kind of definition of consciousness, look at, some science of consciousness, how we can develop mathematical theories of consciousness, and then sort of explore a little bit about machine consciousness. And then at the end, I'm going to sort of tie it all together, I hope in a sort of elegant way, by looking at the relationships between intelligence and consciousness. Yeah. So there's kind of like natural intelligence, natural consciousness, and also kind of AI and artificial consciousness. And this is kind of the weakest bit of the talk, to be frank with you. I mean, I've kind of done a lot of work on intelligence now, done quite a lot of work on consciousness. And really the sort of short answer to this is that we can wave our hands and make a few ad hoc remarks. We really need to do is kind of use mathematical measures of intelligence and mathematical measures of consciousness, and then we can actually do this kind of work properly rather than just, a bit of armchair philosophizing. But I'll do my best. And particularly when it comes to AI and consciousness, there are some maybe interesting relationships we can tease out. Yeah. Okay, so let's start off with just a little bit of background on intelligence and what we mean by intelligence, that kind of stuff. Yeah. So it's kind of one of these kind of complex, multifaceted terms. Wittgenstein had this kind of, sort of what's called sort of multiple kind of. I'll tell you, I'm tired. Family resemblance concept, right? So you have this kind of notion of a rope with sort of multiple strands kind of twisted together. So intelligence definitions are a bit like that. Each one kind of touches on something we kind of feels a little bit like intelligence, but none of them really capture the whole thing. Yeah. So this is like a list from Bartholomew 2004. We got things like cognitive ability, rational thinking, problem solving, goal-directed adaptive behavior. And there's actually a rather nice summary by Legg and Hutter, I think, that kind of goes to like 75 definitions in psychology kind of thing. If I can give you the reference if you're interested. Yeah. So goal-based definitions are quite popular. And the idea is that intelligence is like, the achievement of goals or receipt of rewards from the environment. And, Legg and Hutter, there were some of the pioneers in this kind of way of thinking about intelligence. They've kind of developed a way of measuring intelligence based on this definition. Yeah. So if you're smart, you get lots of rewards and you achieve all your goals. Yeah, that's the idea there. Yep. Now, just as a sort of heads up with all these kind of definitions, most of them have been formulated with human beings in mind. And then they generalize very poorly to animals and even worse to artificial systems. And what I'm kind of after here is not something that just works on humans, like more of the sort of old school definitions are kind of oriented towards. I'm interested in definition of intelligence that applies to artificial intelligence and to bats and to humans as well, kind of thing. Yeah, want something that kind of covers the whole spectrum. So most of the limitations of these previous definitions come about because they've just been thinking about humans and they haven't thought about all the obvious exceptions that occur when we go to artificial systems. Yeah. So with goals and rewards, for example, you have this problem of kind of arbitrariness. Yeah. So humans are kind of pretty much hardwired to, we want to mate, we want to eat, we want to look at beautiful sunsets, all that kind of stuff. And most of that's pretty hardwired, right? We can't just change our goals arbitrarily to like looking at Earth, for example. Yeah. But with AI systems, they can modify their goals, as they like, pretty much. So if we're kind of basing our measure of intelligence on achieving goals and getting rewards, then AI systems can basically rewire themselves to change their goals and rewire themselves to give themselves arbitrary rewards. This kind of wireheading kind of issue. Yeah. And a more deep problem with this whole kind of link between goals, rewards, and intelligence is the problem of actuators. Yeah. If you need to, suppose you've got two systems and they've kind of got the problem of moving this heavy object, up a slope. Yeah. Both systems might be equally intelligent. They might be able to calculate how this rock could be moved up the slope, but one might be like some kind of puny, weak, robot. The other might be like dead strong robot. And then the dead strong robot's going to be able to actually achieve that goal and get the reward, whereas the weak robot isn't, even though they're equally intelligent and both can figure out how to actually, get the thing done. Yeah. So rational thinking, a lot of people talk about rational thinking and cognitive ability. This is from Bartholomew as well. So cognitive ability is kind of, defining the thing in terms of something that's kind of the same, right? And rational thinking doesn't make any sense either, really. We can write programs like in Lisp, for example, kind of are very rational, but we can write a load of really stupid programs in Lisp. Yeah, so there's not really a close link between either of these and intelligence, I don't think. So faced with all this, family resemblance, all these overlapping but not really consistent definitions, people like Gardner and Warwick kind of try and expand it and say, well, no, we've actually got lots of different types of intelligence. We've got musical intelligence, emotional intelligence, so on. And then Warwick kind of tries to generalize to animals and machines by talking about a high dimensional space of abilities. And then people, in animals and machines at a certain point in this space of abilities kind of thing. Yeah? Another important distinction, which can come back later, is this between fluid and crystallized intelligence. Yeah, introduced by Cattell. So fluid intelligence is like the ability to solve new problem, basically. Yeah, if you put in a new environment, then maybe you can solve problems in that environment, and that shows you've got high fluid intelligence. Whereas crystallized intelligence, we're either reproducing stored knowledge, but also we're using heuristics that we've developed to solve problems in another area. So I might have a good way about solving number sequences and get some nice heuristics for doing that. It's a classic IQ test problem. And then when I come to a new number sequence, I can try all the different heuristics I've learned in the past to kind of try and solve that problem. So crystallized intelligence covers both these things. Yeah. Modern research think, fluid intelligence is the be all and end all. They kind of ignore heuristics, but this distinction is still relevant, and I'll come back to it, as I said. Yeah? So I haven't got time to go through all it. I'm just writing a book chapter that kind of goes through all this in much more detail. But at the end of the day, I think it's pretty clear we don't have a clear definition of intelligence. Yeah, but that's never stopped us in the past from measuring intelligence in humans. Yeah. Because in humans, we can order humans on a sort of an ordinal scale, right? Going from the least intelligent to the most intelligent at a very rough level, yeah? you know, the people who kind of, you know, publish papers in Nature and, you know, get high grades at school and, you know, get a PhD at MIT or whatever, we put those at the top of the scale. And then the people who do less of that stuff, you know, go in the middle and the bottom. Yeah. So we can order humans according to their, what we perceive to be their intelligence. And then we find that things like IQ and G-score, you know, correlate fairly well to this kind of ordered set of humans. Yeah. So we can still measure intelligence, even if we don't know what it is, in humans, because we can have this nice ordinal scale. But we can't do the same thing with animals, right? I mean, there's a bit of stuff about, you know, crows being more intelligent than snails, for example. But, you know, really, when it comes to animals, it's much more loose. And when it comes to AIs, we're completely in the dark. Yeah. So we can't just sort of easily measure intelligence in AI systems because we've got no way of grounding that measure in anything else. Yeah. Okay, so that's why I'm doing what I'm doing to some extent. And then I'm going to make a case for actually thinking about intelligence and its, in terms of prediction. I should have started my clock ages ago, actually. And then this, I think, is a much clearer and neater way of thinking about intelligence, and then also enables us to understand why all these other definitions make some kind of sense. Yeah. What got me started on this relationship was this kind of predictive brain hypothesis. So I don't know if you've read Clarke's book, Surfing Uncertainty, but there's an awful lot of interest these days in the idea that what the brain does is fundamentally prediction. Yeah. So in the sort of old school model, Mac had his sort of 2.5 and, you know, 3 sketch and this kind of thing. These kind of older models, which I, you know, did a lot of work on, as it happens, you know, back in the day. You know, the idea is that you have these hierarchies, right? Just like a deep neural network that does visual processing. The bottom of the hierarchy might be sort of simple edge detectors, and then maybe a little bit further up you've got corners and maybe squares or whatever. A little bit further up you've got the hands and the eyes and the noses, and then right at the top of those sort of hierarchy of layers you get, you know, the Bill Clinton neuron that only fires when it sees Bill Clinton, or the Jennifer Aniston neuron that only fires when Jennifer Aniston's around. Yeah, and these have been found, right? They've stuck electrodes in people's heads and found the Bill Clinton neuron. Yeah. So that's the sort of the old model of the brain, like this hierarchy or hierarchy of layers with increasing abstraction as you go up the layers. Yeah. But then the predictive brain hypothesis flipped this on ahead. Yeah. So instead of there being like a flow of information upwards, the idea is there's a flow of prediction downwards. Yeah. So each layer is trying to predict what's happening in the layer below. And then what's getting passed up is not like the information about the edges in the image or whatever, it's the error about the prediction. Yeah, so it's trying to predict, and then we're getting prediction error flowing up, and then that improves the prediction. And so you get this kind of top-down sort of predictions moving downwards, and then the error signal moving up. And that sort of correlates, sort of is consistent with the sort of this the fact that there's lots more top-down than bottom-up connections in the brain. Yeah. Now this is a very sort of compelling, sexy hypothesis, right? A lot of people get really into it. Yeah. There's actually no real good evidence for it, but you know, at the same time, you know, you read Clarke's book or some of the other books in this area, and they kind of, you know, they kind of convince partly. Yeah, it's a nice interpretation of the evidence. The truth is probably more like this is some component of how the brain works, but it's not the whole picture. Yeah, most of these like neat theories are partial at best. Yeah, but still, you know, if we buy into this predictive brain hypothesis stuff, then we've got a very nice link between intelligence and prediction, right? When we're looking at brains, yeah, because if brains are intelligent and the brain's core function is prediction, then brains that are better predictions are going to be better predictors, are going to be more intelligent. Okay, so that's the argument for the predictive brain hypothesis. When it comes to action, we're constantly using prediction in order to plan our actions and achieve our goals. So again, we've got this neat tie-up between prediction and goal achievement and reward achievement. Yeah. So, you know, if I feel like spaghetti tonight, I might sort of imagine all the different shops that have spaghetti. I might predict the stocks of spaghetti right in a pandemic, and I might, you know, predict, you know, which shop I should go to, how I'm going to get there, whether I'm going to get mugged on the way to one shop with spaghetti, which shops can have the best spaghetti, and so on and so forth. Yeah. So pretty much any kind of area in our life where we need to do something, we're carrying out complex sequences of predictions that enabling us to do it, right? And these are predictions that exist on the time scale of years and the time scale of microseconds when we're kind of, or milliseconds when we're doing like fine motor movements with forward models and all the rest of it. Yeah. So if you can't predict, you can't plan, right? So basic animals like snails, right? Stuff happens to the snail and then, you know, it suffers and it dies or it manages to live. It can't like predict what's going to happen as it goes around the corner, whether it be some tasty lettuce there or something. Yeah. So systems that are more intelligent are much better at prediction, and that enables them to get much more control of their environment, and much more control over, you know, what they do, whether they get their goals and rewards and all that. Yeah. And you can sort of extrapolate forward, right? You can imagine, well, what would happen if we had like perfect predictive ability, like God, you know, God can see, you know, the fate of humanity 1,000 years into the future. And so that gives you some kind of awesome power and intelligence, right? Because you can tell exactly what's going to happen to every single person and what they're going to do, you know, setting aside the problem of free will. Yeah. So we've got some nice kind of fictional examples of this, right? So Next, I watched, a couple of months ago, whatever. So in Next, Nicolas Cage, right? You can see 2 minutes into the future on things that relate to his sort of personal life, yeah. And even with just 2 minutes of perfect omniscience, he can do a whole load of stuff that ordinary people can't do, right? He can win any fight because he always knows who's going to hit him when. He can sort of manipulate people to some extent because he knows what they're going to say next. He can win stuff at gambling and so on and so forth, yeah. So he's got quite a lot of power given to him by that extra predictive ability, and that would sort of appear as intelligence if we didn't know that he had some kind of magical power, yeah. Then we got these kind of time loop films of the same kind of idea, right? These people are sort of re-experiencing the same day time after time. And so because they have worked through the day multiple times, they can kind of predict what's going to happen at different points and do lots of clever stuff in terms of manipulating people or avoiding situations that are difficult and so on and so forth. Yeah. So again, you're becoming sort of super smart in that environment because you can make really accurate predictions about what's going to happen in that environment. And animals, we can tell a similar story, right? So again, I've mentioned the humble snail, right? Stuff happens to the snail, and then it's got some evolutionary hardwired stuff that means that snails on average live, survive as a species, even if a few snails get crushed along the way, yeah? And then we got kind of tool use in crows and octopi. And tool use is a classic kind of predictive problem, yeah? Firstly, you've got to be able to sort of see into the future about having some idea about the tool in mind and how it's going to let you solve a particular problem. Then you've also got to know that a piece of wire, for example, can be bent into a hook, whereas a piece of wood can't be bent into a hook. Yeah. And so there's a classic example of this crow that can there's a sort of tube of peanuts in a tube, and it bends a wire into a hook and then lifts the peanuts out the tube. Yeah. So again, that's a whole series of predictions the crow's doing that the humble snail's incapable of doing. Yeah. And obviously, we're combining both reactive behaviors and complex predictions on multiple timescales. Yeah. Now, intelligence environments. Okay, so a lot of people working in intelligence think that it's just some kind of abstract general property that someone is intelligent or they're not, particularly when it comes to fluid intelligence. And that regardless of whether they're working in the natural world, studying a genomics database or whatever, or doing plumbing, let's say, they've all got the same level of intelligence regardless of their environment. Yeah? But actually, predictions is relative to an environment. Yeah. We can build these awesome supercomputers to predict weather patterns, but those same supercomputers to predict weather patterns are absolutely hopeless at protein folding, right? Because they're just not designed to do that, yeah? And we actually haven't got a completely general prediction system that can outperform systems built for specific environments. We don't really have anything half viable that will work across any environments at all. Yeah? Environments are wildly different in complexity and patterns and all the rest of it, yeah? And even the humble human brain, right? We've been honed by evolution to work in a hunter-gatherer environment, and we can generalize partly, we've mostly functioned in civilization, right? But, but we've got limited working memory. We've got very limited capacity for, high dimensional thought and all the rest of it, yeah? So in other environments, we completely suck, yeah? And Cholle, which I'm giving a reference to, I just read a paper by him, and he makes kind of this point quite nicely, actually, yeah? And obviously AI systems are the same, they're highly specialized, yeah? So I think, both for intelligence, but also particularly for predictive intelligence, I think we have to accept there's lots of different forms of natural and artificial intelligence, and each of these forms only work within a specific sets of environments, yeah? And instead of doing this sort of Gardner and the kind of Warwick route, we don't have to broaden our concept of intelligence to handle this. Instead, we say there's a single thing, predictive intelligence, and that predictive intelligence actually each predictive intelligence works well within a particular set of environments, yeah? So system A has a high level of predictive intelligence in a musical environment. System B has a high level of predictive intelligence in a chess environment, for example. Yeah. And this is nice, right? I mean, this gets us a nice conclusion. We can actually understand and appreciate different forms of human intelligence. So when we come back to the kind of the IQ tests and all this kind of stuff, we can see, well, actually, they're not just measuring intelligence in general. What they're doing is measuring intelligence with an academic environment of mathematical symbols, abstract shapes, and so on and so forth. Yeah. So that's why we're getting this correlation between IQ tests and the results of IQ tests and the measures of academic success. Yeah, that's why people who publish papers in Nature get high IQ, because IQ is measuring academic intelligence. Yeah, but then we can look at other sort of trades, professions, and so on and so forth, and say, well, actually, these guys have just as much predictive intelligence, but it's just not working in academic environments, working in a plumbing environment or electrical environment or some other different environment from this sort of academic one, yeah, with all the sort of abstract symbols and so on. So that's quite a nice thing, I think, yeah. So this leads me to sort of the four kind of hypotheses about intelligence I'm going to be arguing for so far, yeah. So firstly, H1 shouldn't be a surprise by now that prediction is the most important component of intelligence. I just argue for the claim that prediction and intelligence are relative to sets of environments. And then we can say, well, the amount of systems crystallize intelligence varies with the number of accurate predictions that it makes in a set of environments, right? This is kind of leading forward to how we can actually measure it, right? If we're making more predictions that actually come true, then we're obviously a bit smarter in that particular environment, yeah? And then we can define fluid intelligence as the rate of change of crystallized predictive intelligence, right? So that's a sort of neat way in which we can tie the two things together with this kind of whole predictive thing, yeah? So that's the core of what I'm trying to argue in this section. And if you sort of buy into that, which you might or might not, yeah, we can have a discussion about that, then we can actually devise an algorithm that lets us measure predictive intelligence. And then we can have what people have been sort of aspiring to, you know, with these different, I haven't had time to do write a background on this, give a background on this, but people like Legg and Hutter, Hernandez Arroyo, and a few other people have been trying to come up with universal measures of intelligence that work across all different kinds of systems. So we can, for example, compare an AI's intelligence with a, sheep's intelligence, let's say, and with a human's intelligence. Yeah. So this is kind of tapping into this kind of work and trying to say, well, actually, if we buy the relationship between intelligence and prediction, then we can actually develop an algorithm that can be used to measure predictive intelligence across all kinds of different systems. Yeah. That's kind of what I'm saying. So we can compare, yeah, kind of, right. So that's what I've been doing, and I'll go through it a little bit. I'll try not to get too much, I won't get bogged down in the details because I'm going to run out of time. So I've developed this algorithm that in theory can be applied to any system at all. Obviously, make it work on humans, we're going to have to, maybe estimate it rather than actually directly measure it, as you'll maybe see when I start going into it. And I've actually tested it on an agent in maze environment and deep learning algorithm. I'll just briefly show you the web page of this with those experiments on, I'm not going to go through them in any detail, yeah? So just to explain how it works, I'm going to probably go a little faster. I'm just going to skip little bits because I know I'm going a bit more slowly, and I don't want to like go on forever. So suppose we've got a simple agent, right? So this is a sort of classic sort of agent, right? It's got these internal states, I1, I2, I3, and I4. The sort of zeros here are the points in time, yeah? And as it interacts with its environment, it's got sensors, yeah? And that's changing in the internal states as it sort of interacts. Yeah, so these internal states are changing as it moves through time and space and getting different data from its environment. Yeah. So this agent's developing predictions as it moves around its environment about what's going to happen next in its internal state. So this is an internalist definition of intelligence because each agent has a different relationship with its environment, different sensors. What a worm experiences as it goes through a room is very different from what a human experiences. Yeah. So we need to have an internalist definition here rather than trying to define it in terms of states of the environment. We have to define it of how we're sensing the environment. Yeah. This agent's generating time index predictions. So, for example, it's saying that at time 3 here, I don't know if you can see my mouse, but hopefully, I1 will have this particular state. Yeah. And these predictions are probability distributions, just like humans, to get the most general case here. Because when I say, that this shop will have spaghetti, I'm making some kind of, there's a probability of that. It's not exact, right? And also it's probability in terms of, what it has, but also when it will have it. Yeah, there's states and time. There's kind of these probability distributions. Yeah, doesn't worry too much about that. It's doing that all the time, basically. Yeah. So if we want to measure predictive intelligence, we can compare these predictions with future states of the same agent. Yeah, it's saying that this state, internal state, will have this future value at a certain time, and then when it reaches that time, we can compare that value with the what was predicted at the earlier time. Yeah, so we're comparing, for example, P12 with I12 here, because this is a prediction about the state of I at time t2. Yeah. So in order to measure our predictive accuracy, we need some kind of method for comparing the probability distribution of the prediction with what actually happens. Yeah. And for discrete probability distributions, we can use Hellinger distance. Yeah. So Hellinger distance is quite nice. It's basically, there's various methods there's like Kullback, Liber, divergence, and there's various other methods for kind of comparing probability distributions. But I picked Hellinger distance because I'm trying to get a number that is between 0 and 1. So I don't have scale issues with this algorithm. Yeah. So this gives a number of 1 when there's a perfect mismatch between two probability distributions, and it gives 0 when there's a perfect match. So if I want to measure the accuracy of predictions, I need to take 1 minus Hellinger distance. Yeah. I probably won't bother with this, but we have to take a slightly different approach for continuous probability distributions and discrete values. Yeah, we have to put an error bounds and then look for a match between the standard normal. But let's not worry too much about that. Yeah, all you need to know is that we get a number between 1 and 0 that tells us how accurate the prediction is. Yeah. Now, one thing we need to get rid of, which isn't considered too carefully in some of the other work in this area, is we need to get rid of random guesses. So when I implemented this initially, I found that my agent can actually basically put a equal distribution across the different states it could be in, and that random guess is pretty good. It gave it like gave it a pretty decent chunk of intelligence for doing virtually nothing. Yeah. So we need to kind of eliminate random guesses. So we just subtract what would happen with a random guess from the prediction, from the match between the prediction and what actually happens. Yeah, so that's just doing that really, and we can similar thing with the continuous distributions. Now, one thing we need to take into account when we're trying to measure prediction accuracy is the complexity of the predictions. Yeah, so we might have a system that is completely disconnected from its environment, for example, and has like 20 internal states, let's say, and then it might predict that these internal states are going to stay the same, for the next 10,000 years, right? So there's a whole bunch of predictions being made, and they never change. And if all we're doing is measuring prediction accuracy, that system is going to do brilliantly. Yeah. So we need to kind of get rid of that. And here I'm going to use Kolmogorov complexity, which briefly, I'm sure you're mostly familiar with that already, but it's the shortest, it's a length of a program. It's the length of the shortest program describing a particular string. Yeah, something approximately that. Yeah. So, and again, I want to kind of get this to a number between 1 and 0. So this is kind of the length of the shortest string describing the predictions divided by the length of the string describing the predictions. Yeah. So I'm basically, this will always end up between a number between 1 and 0. So a highly compressible string will make this a very short, very small number, which will then obviously, offset large numbers of trivial predictions. Yeah. So what we do is the agent moves through all different states of the environment. We sum up the accuracy of its predictions. We multiply that by this, this sort of compressibility factor to take into account the complexity of the predictions. And then we take the log because I want to compare, an ant with super intelligence, and to do that it's easier if they're not like wildly out in terms of numbers. Yeah. So the final thing we need to do for this measure is we need to sum the intelligence across a set of environments. So intelligence is always relative to a set of environments. It might not just be one environment trying to measure. Might want to measure on like 5 different mazes, for example, or 5 different time series. Yeah, for example. Yeah. So again, we have this problem that we might have 2 environments, and they might be like really similar to each other. There might be a really trivial difference between the environments. And if we add the intelligence in a simple way between the 2 environments, then we're doubling the intelligence without really there being double the intelligence. Yeah. And in the other case might be these are wildly different environments. And then we would need to, we're still doubling the intelligence. So we're not really taking into account differences between environments. Yeah. So here we're taking the Kolmogorov complexity of the environments considered together divided by the sum of the Kolmogorov complexity of the environments considered independently. Yeah. So obviously if we have 2 environments that are really similar, this will end up being a half. If we've got 2 environments that are really different, then this will end up being 1. Yeah, so it's a way in which we can, weight the sum of the across the environments by the differences between the environments. Yeah. So what I'm using for this is Payoff, this sort of symbol here. So it's sort of the rune I'm using to describe it. So we're all kind of a bit sick of, we're all a bit tired of all these Greek letters. I'm going to mention pi a little later, which you may be familiar with. Yeah. So we've gone through the Greek letters 20 times. They all have 5 different meanings. And I used to work with a guy from Norway, right? And so in a previous work, we developed manas, which is based on H, I think it was, the rune for H. So I figured we'll go with runes for this one. So it's called Payoff Perth or Pertho. And it's quite nice, this, because runes, as you might know, have these kind of magical, mystical meanings to them. And so Payoff is associated with a dice cup, chance, secrets, destiny in the future, which I thought was massively appropriate. I picked it because of the P, but it turned out it was kind of good in other ways. And then so we've got Payoff _ C for crystallized intelligence, and then Payoff _ F for fluid intelligence. Yeah. Okay, so what I've just outlined is a sort of way in which, and it's not perfect, I'm sure it can be improved, it's a way, but it is a universal way of measuring predictive intelligence across a range of systems, and I'll touch on a few applications in a sec. Yeah. And also I'll come back to it when we're trying to compare, when we're trying to understand the relationship between intelligence and consciousness. Yeah. So I have, to test this, I mean, as a sort of proof of concept as much as anything, I think I'm still showing it. Yeah. Okay. Yeah. So there's a website I built, and the beauty now, right, is we can run TensorFlow in JavaScript in the browser. So I kind of, I implement it on a bunch of different time series. I've got, even got UK coronavirus from, a couple of months back. And what it's doing then is it's a sort of deep recurrent neural network, and you can train it, so you can play around with this stuff. It should work. I mean, I've tested it fairly well. And so you can sort of train it. I actually tested this, but we can train it, and as it trains, it'll measure the intelligence, the predictive intelligence, by comparing the predictions about, the particular time series and what actually happens in the way I explain. And then if we sort of click on a particular thing, it's not the UK coronavirus, well, it was stuck with coronavirus at the moment because it's training on that, but we can then sort of see the sort of prediction match and how it's doing all the calculations. Yeah, so that's the, I'll just stop that. I'm not going to go through these in any detail. But then I've also implemented like an embodied thing. I've got an agent and maze environment. It's kind of the same thing. It's learning to make predictions about future states, and then the intelligence is being measured across a sort of range of different mazes. Yeah. So this is kind of just really a proof of viability, and it kind of works nicely. It works in real time on a browser, so I'm fairly confident there's not major sort of scaling issues. But obviously, when we get to the human brain, we have to get estimates rather than the real thing kind of thing. Yeah. Okay. Oh, no, bother. Right. Okay. Let's just go down. Okay. Okay, experiments. Yep, done demo. Okay, great. So obviously, one major application for all this stuff is comparative work on intelligence. Yeah, we want to be able to compare humans with AI systems. Yeah, and that comes sort of down to the bottom point, actually, just jumping about a bit here for AI regulation. Yeah, there's numerous discussions of singularity and the fear about the robots taking over and hacking into our cybersecurity systems and all that. So if you want to regulate AI, you have to be able to measure it. Yeah, this sort of armchair scratching your chin business isn't going to do the job. Yeah. So if we want to, for example, prevent computers from hacking into our nuclear missile codes, then we need to limit intelligence, predictive intelligence in the area of cybersecurity. It's always relative to sets of environments, right? We might want brilliantly intelligent, super intelligences in the area of protein folding, or some other area that's useful to us, or cancer diagnosis, whatever. But we might want really stupid AIs when it comes to when it comes to cybersecurity or manipulating people's psychology and all the rest of it. Yeah. So this is a way in which we can meaningfully regulate AI if we want to do that. Yeah. And again, I'm jumping about a little bit here, but in terms of regulating AI, most people are sort of just don't think very carefully about what's meant by AI. Yeah. Most people think that, say, classifiers are, artificial intelligence. I'm not going to go into that now, but I think there's good reasons why they're not. Most people think that sort of, something like Alexa is a form of artificial intelligence, but it's not. It's not doing any kind of prediction, right? It's conversational design, right? There's no intelligence whatsoever really in Alexa, except maybe in the text, voice speech to text. Yeah. So some AI systems have a lot of intelligence, like AlphaGo, for example, Deep Blue maybe. But other systems that are called artificial intelligence really aren't artificial intelligence at all. They're like classifiers. So if you want to do proper regulation, you need to be able to measure artificial intelligence. You also need to be able to say which systems this regulation applies to in a very precise way. And that's why we need something like my predictive measure and something like my predictive definition. Yeah. And this is slightly whimsical, but not entirely whimsical, the development of an AI singularity. So the idea of an AI singularity is that we design an AI system that is itself capable of designing an AI system that's more intelligent than itself. And this more intelligent AI system then goes on to design a more intelligent AI system. And so in theory, you could get this sort of explosion of intelligence. This is the sort of thing talked by Nick Bostrom with his superintelligence, and David Chalmers, and I think Murray Shanahan. I haven't listened to his book yet, but he's got a book on the singularity as well. Yeah, so that's the AI singularity. But of course, it's mind-numbingly hard to design an AI system that in itself can design an AI system that's more intelligent than itself. But another way of doing this, producing sort of accelerating artificial intelligence, is if we can use a feedback signal that tells the system how intelligent it is. Yeah, because if we use my measure, for example, to tell a system that it's behaving in a really intelligent way in this environment, i.e., making lots of accurate predictions, then we can then use genetic algorithms or something, or reinforcement learning in combination with that feedback signal to develop systems or automatically, if you like, develop AI systems that develop to become more intelligent. Yeah, because we've got the signal now that enables them to evolve along, using the signal of their intelligence. Yeah. So in theory, we could potentially develop an AI, a sort of system that increases in intelligence all by itself. It's not going to be a singularity realistically, and it's only going to be limited to a set of environments anyway. It's not like I put the Terminator thing there somewhat whimsically. Yeah, it's not probably going to become the Terminator. Yeah, and I've actually got one of my students doing a project on this at the moment. Yeah, so hopefully, he'll be able to have some kind of concrete experiments by the new year, and we'll have some, be able to stick a quick paper on it. Yeah. So that's the development of the AI singularity, and then I kind of touched on the regulation, how we can use it, how we can measure this to actually prevent such a thing from happening if we wanted to. Yeah. Okay, so I thought we're kind of about halfway through here. So has anyone got any kind of quickish questions, or shall I just drive on to the end? I don't really mind. Yeah.
I think it's easier for you to continue, and at the end we take like 15-20 minutes of questions. Okay,
that's cool. Yeah, that's fine. Yeah, that's probably easier actually because I've got my flow now. Yeah. Okay. Righty-ho. So that's the intelligence stuff. Yeah. And now I'm going to sort of go into the consciousness stuff, and I don't unfortunately have a neat and tidy measure of consciousness, but I think I know how we can get one. So that's the sort of good news. And the bad news is it's going to take an awful lot of work. Yeah, but the real problem with consciousness is not so much is actually getting to the stage when we can see how we can actually get a way of measuring it accurately. Yeah, and that's kind of a lot of the work I've done in the last 10 years has been kind of oriented towards getting to the point at which we can actually do the science of consciousness properly. Yeah? So the question I always have to deal with when talking about consciousness is, what is it? It's a fair question. And so, so we really have to start, and as I'm going to say, to understand what consciousness is, we need to really understand what the physical world is. Yeah. And most of the time, people make the mistake of confusing their consciousness with the physical world. And then that is half the problems of consciousness are linked to that kind of problem. Yeah. So most of the time, right, we're just immersed in this world of colorful, noisy, moving things, right? I'm sort of looking around these sort of lights, and this computer and all this kind of stuff. And most of the time, because it's normal and natural, we take what we see as being the actual physical world. Yeah. And this is basically the position known as naive realism. Yeah. And I do this all the time, and I'd be very surprised if any philosophers of consciousness did anything different, frankly. Yeah. So as we're sort of cycling across the Golden Gate Bridge, I mean, prepared one version of this talk, when I was in San Francisco, we look at the red of the bridge and think, yeah, the bridge is red, right? It's a reasonable thing to say. And we hear the car going past, and we hear the noise of the car, and say, wow, that car is making that particular, throaty roar because it's, some kind of expensive American car. Yeah. So as we look around the world, we're kind of experiencing colors, sounds, smells, tastes, and so on and so forth. And we very naturally attribute those to the things that we see around us. Yeah, this is naive realism. But within naive realism is fragile. It's fragile because we kind of know how the brain works a bit now, but it's also fragile because there's stuff that happens in our naive encounters of the world, and we try and explain it in somehow. Yeah, and this is where the physical world comes in. Yeah, we can't sort of fully explain why stuff happens in this sort of world of naive realism because it just sort of happens. It's kind of structured that way. We could sort of describe it mathematically. But typically what we try and do is come up with something that sort of lies behind the scenes, so to speak, and explains what we're actually experiencing. Yeah. And this is where the physical entities all come in. Yeah. And what I call them is invisible entities, kind of tying up with Metz again a little bit. And these are some examples. Yeah. X-rays, atoms, modern physics. And I'll go through a couple of examples to kind of explain what I mean. Yeah. Okay. So originally with X-rays, they had these kind of photographic plates lying around. They had some radioactive materials lying around, and they were kind of a bit puzzled that when they put them together, these radioactive plates kind of change colors, right? They had these weird patterns on them, yeah? And so they had no idea. They couldn't see anything happening, right? There was nothing that they, in their experiences, that could possibly explain how this lump of, uranium 235, whatever, was actually causing these photographic plates to change, yeah? So what they did is they came up with something. They had the idea that perhaps invisible to us, beyond our senses, there's something happening between this radioactive source and these photographic plates, some kind of interactive between them. And so that's why we get this kind of X-ray. I mean, the very name X-ray suggests, unknown ray, right? So now as this sort of chap that lies on this sort of X-ray bench, we now have a perfectly good understanding about how this thing's releasing these X-rays, and they're sort of electromagnetic waves, and they're passing through, and they're absorbed by different amounts by bone and soft tissue and so on and so forth. So but we never see any of that. This is all an invisible explanation that explains how we can go from this guy on the left to this particular picture on the right. Yeah. So I haven't got a particularly good thing on atoms, but back in the 17th century, it was the same kind of idea, right? They sort of saw these regularities in the world around them. Newton was coming up with these laws, and they just started rereading Lucretius. So they had this idea of the physical world consisting of these kind of atoms bouncing around the void, and then they tried to use these atoms bouncing around the void to kind of explain what they're actually seeing in their sort of physical experiments. Yeah. So again, the atoms are performing this kind of task of an invisible explanation. And then now, obviously, modern physics is full of this stuff, yeah? We've got four-dimensional space-time, 10-dimensional superstrings, wave particles, and so on and so forth. None of us can imagine a wave particle. We've never seen one in our life, right? But we kind of believe in the whole quantum theory thing because it makes these beautiful predictions about what happens in our experiences, yeah? And so all these are invisible explanations, yeah? And if I'd had time, there's a nice quote by Russell talking about how matter is like, the source of events, but not something we can ever actually experience, yeah? So this is possibly slightly controversial, but I think it's true, is that the physical world's invisible. We can describe it mathematically. But we actually don't have any direct experience of physical things, yeah? We experience consciousness, everything in our naive encounters of the world that's non-physical. So colors, smells, sounds, etc. There's no place for those in the physical world. There's no such thing as a color in the physical world. But there is, place for it in our consciousness, yeah? The non-physical colors, smells, sounds, etc. properties of consciousness, yeah? So this is sort of everything that we're experiencing there is our consciousness, yeah? And behind the scenes, so to speak, we have these hypotheses about wave particles, electromagnetic waves, and so on and so forth, that kind of enables us to understand how this can kind of come to be and how it works. Yeah. A slightly more positive definition of consciousness is as a bubble of experience. So this is kind of being drawn from kind of phenomenology. Yeah. So we kind of look out from our bodies into this world, but we don't experience the whole world, right? We only experience like a limited bubble of space that sort of shapes, fits the surroundings. So my consciousness is currently in this sort of room environment you can't see, and I'm kind of spinning my fingers and this kind of stuff. And this is changing every couple of 100 milliseconds roughly, yeah? So this bubble of space, roughly centered on our bodies, we look out from our bodies, this bubble of space, and this bubble of space is populated by the properties of consciousness like color, smell, sound, etc. Yeah? So I think it's kind of fair enough to kind of describe consciousness as this kind of bubble of experience that emerges when we kind of wake up in the morning, disappears when we fall into deep sleep at night, and appears in this kind of fragmentary form, during dreams and this kind of thing. Yeah? And so the whole work of people like Husserl, Merleau-Ponty, is to describe the structures of these bubbles of experience. And then we're using the invisible physical world to explain and predict regularities in these bubbles of experience. Yeah. And so going back to the atoms and the void, this is kind of when the concept of consciousness emerged. And I'll give you a little bit of evidence for that in a bit. But the concept of consciousness didn't really exist before the 17th century, at least in the Western kind of Europe. Yeah. But it did emerge when people started thinking about atomism. Yeah. So with atomism, you've got the atoms bouncing around, but these atoms aren't colored. These atoms don't smell, they don't taste, right? They don't have any of these kind of properties. So in the 17th century, people like Locke and Galileo had this distinction between primary qualities, which are properties of the atoms, and secondary qualities that are properties of consciousness. So what they were doing is saying, well, here's the physical world with these atoms and the void, but we're experiencing all this stuff in our naively realistic encounters of the world. So they needed to kind of put it somewhere, basically. And so they invented the concept of consciousness, not necessarily consciously, so to speak, to put all these kind of colors, smells, sounds, tastes, etc., that no longer could be fitted inside the physical world. Yeah, so there's kind of this bifurcation between the physical world of atoms and the sort of experience world of consciousness. Yeah? There's a rather nice quote from Wilkes saying, she talks about like Chinese and all this kind of stuff, but in the West, at least in English and other European languages, consciousness cognates is in the present range of senses scarcely 3 centuries old. So this fits rather nicely with this sort of story I'm telling about the emergence of the concept of consciousness. Yeah. So we kind of got the sort of, this is the 17th century kind of bifurcation, right? We've got this sort of world of the primary qualities of the atoms, and then we had to put the consciousness, all the other stuff somewhere. So we kind of put all that in consciousness. And then as we get increasingly abstract to these kind of wave particles and so on and so forth, we can only really describe this stuff mathematically. We have no idea what a wave particle looks like. It doesn't look like anything. So we can't really imagine this anymore, but we still have this consciousness, and we're still using these mathematically described regularities in the physical world to explain what's going on in our consciousness. Yeah. Okay, so that's what I think consciousness is. We can discuss that in the questions if you like. Now, how can we actually study it? This is the sort of more important question in a way. Yeah. So the one problem we got, if we want a science of consciousness, then we actually have to measure consciousness. Yeah. And in the sort of scientific work on the neurocults of consciousness, people do sort of often that's kind of really limited to, is someone awake or they're not awake? Yeah, we haven't really progressed much beyond that in that. A little bit in terms of, Dehaene has all these kind of clever masking experiments, so you can, to some extent, present more complex stimuli unconsciously and consciously and control the degree to which they're conscious and unconscious. Yeah, but that's the kind of where we're at with that. But with all these experiments, we're measuring consciousness through first-person reports. And there's a whole, massive literature on all the philosophical problems with this and a whole heap of bad solutions to this. Yeah. So my own solution to this, which is a good solution, of course, is that we need to make some fairly sensible assumptions about how the measurement of consciousness can take place. And then we can consider the science of consciousness to be true on the basis of these assumptions. Yeah, we're never going to philosophically solve some of these problems. We can just dissolve, if you like, or understand as pseudo problems. But other problems like, is it really the case that any of you guys are conscious or not? We can never prove that, yeah, because we have to, in a way, get the measurement of consciousness started before we can even answer that question. Yeah, so that's why I need to make a few assumptions to get us started. Yeah, and I'm not going to go into all these. I made quite a few of these assumptions. It's all in my book if you're interested. So we need to, for example, assume that identical physical system is associated with an identical consciousness, and then we need to assume that there's some kind of mutual information or correlation between the reports about consciousness and the consciousness, right? So we can actually measure it, and these assumptions have to be limited to systems that we really believe are making accurate reports about. Yeah, so I've talked about developed this idea of a platinum standard system, which is like a a system whose statements about consciousness we believe. Yeah, and this is humans as the sort of paradigmatic case, because obviously if we move into animals, we can't really. It's tricky to assume that they're conscious in the same way. We can't assume that. I don't think. It's certainly we can't assume that with artificial systems, and even with humans. If you've got someone with epileptic autism or whatever, or split brain or something, we can't necessarily assume that their reports of consciousness are accurate. Yeah, so we have to take a sort of paradigmatic system and then study that system and then generalize from that system. That's the idea here. Yeah. There's something that's not really tackled much in the science of consciousness is how we can actually describe it. Yeah. So obviously an awful lot of work, Husserl, Merleau-Ponty and so on, has gone into describing consciousness in natural language. Yeah. But natural language isn't really a good scientific tool at all. It's context bound, it's ambiguous. We can't use natural language to describe the consciousness of infants, bats, robots, and they can't even talk in natural language, and it's not mathematically tractable. Yeah. So we're looking here for a science of consciousness that applies to any system at all in theory. Yeah. So we need some way of describing consciousness that can be used to describe the consciousness of many different types of systems. Yeah. And so natural language doesn't cut it. We need a precise formal way of describing consciousness that can be applied to any system. Yeah. So I've sort of did a little bit of work on XML, liminal. I'll say a little bit about that. So this is Balducci and Tononi's approach to this. They have this idea of a high dimensional structure. They call it quayle, and the sort of shape of this quayle corresponds to the sort of the structure of the consciousness. Yeah, so I'm not fully convinced by this, but it's not a bad attempt. Yeah, it's a mathematically defined structure that corresponds to a state of consciousness. Yeah. In my sort of work on my PhD, sort of quite a while ago now, I kind of had this idea of maybe could use like a markup language to describe, state of consciousness, and it's still got something in it, I think. Yeah. And then obviously I vaguely thought about category theory, but this problem is essentially unsolved. Yeah, we don't have a good way of mathematically describing a state of consciousness, and a lot of work needs to be done to achieve that. Yeah, that's one of the sort of hurdles, if you like, before we can really fully solve consciousness. Yeah. So that's measurement consciousness. Measurement of the physical world is sort of more straightforward. Obviously, in a way, we're always measuring the physical world from within consciousness. At least humans are. Robots possibly not. And so within consciousness, we have these kind of calibrated sort of objects. Like in the simplest case, you might have a stick that's the same length as the platinum standard meter rule that's used to be kept in Paris. And then we can compare that stick within our consciousness to an elephant, for example. And then because this is calibrated against a set of measurement units, we can say that the elephant is like 3 meters high, right? And there's quite a lot of discussion and theory about all that. Yeah. But we can kind of agree that we can pretty much measure the physical world within our consciousness by comparing it with these calibrated objects. Yeah, it's fairly straightforward, I think. Yeah. Now, another aspect of this is again rather a lot of work on let's say computational correlates of consciousness, or cognitive correlates of consciousness, or functional correlates of consciousness, and in case of Tononi, informational correlates of consciousness. Yeah. Now, again, I don't have time to go into all the arguments for this, but it turns out, let's say, a sort of hand-waving gesture, that there's no such thing as a computational or informational correlate of consciousness. Yeah, and the reason being is that computations, functions, and information are actually observer relative. There's no such thing as a computation actually occurring in the physical world. Computation is like an interpretation of the physical world, and information is kind of the same thing. Floridi's done some very nice work on this. He talks about information as kind of interface, where we define this interface. Once the interface is defined, then we can read measurement. We can take information states out of a system, but the interface itself is observer relative. Yeah, there's no such thing as information again in the physical world. And again, we can discuss that later if you want. Yeah? So if we want to do a science of consciousness, we have to measure physical states of the system. Yeah, electromagnetic waves, possibly neuron firing patterns, whatever, but definitely not computational or functions. Yeah. So this is where we're at the moment. A lot of scientific work on neural correlates of consciousness. There's been some nice review papers on this. A lot of work on this. If you go to the ASSC, the Association for Scientific Study of Consciousness, then there's usually 1 or 2 people giving some nice, recent work on this stuff. Yeah. So people looking for synchronization, connection patterns, etc. They're present when consciousness is present, absent when consciousness is absent. But I'm more of a Popperian, right? Yes, your research on the neural correlates of consciousness yields useful data, but we're not just looking for a long list of correlations between, states of the physical world, the states of consciousness. If we want to do a science of consciousness, we need a compact mathematical description of the relationship between consciousness and the physical world. Yeah, that's what all the good scientific theories in the past have been about. Yeah. And so I've got this idea of a C theory, which is like a mathematical description of the relationship between measurements of consciousness and measurements of the physical world. So let's just give an example just to show how it works. Yeah. So that here we have like a physical brain. We measure the physical brain, and we have a description of the physical state. Yeah, and this might be a sort of mathematical description of some kind. Yeah, you know, like we have in physics. Yeah. And then we have a human, and with that human, we can actually, if we believe that human, we make certain assumptions, we can actually get a report of their conscious states, and we can convert this into Balducci-Antononi's query or an XML description or something along those lines. Yeah. So we have two complex, mathematically described objects, if you like. Yeah. One a description of the physical world, and one a description of consciousness. And the C theory is something that maps between these two descriptions. Yeah. So in theory, we could generate a prediction about what's the physical state associated with a particular conscious state, and a prediction about the conscious state associated with a particular physical state. That's the idea here. Yeah? And we have an example. Yeah. So this sort of didn't come out of nowhere. I was sort of inspired in my thinking about this by Tononi's information integration theory of consciousness. Yeah. So what he has is a sort of fairly, he was on version 3 last time I checked, but maybe he's on version 4 now. So he had this kind of mathematical algorithm that links a description of the physical world to a description of consciousness. So it's a sort of one-way mapping, really. You have a set of elements that have a sort of state transition, and then you apply the algorithm to the state of elements, system of elements, and then it will identify which part of those elements is associated with consciousness. I mean, it's a prediction, it's just a theory at the moment. And it tells you how much consciousness is present. This is like the phi value of 45, for example. And then you can analyze that same set of conscious elements, the sort of thing in this sort of reddish orange color. And then that's how he generates his description of consciousness. Yeah. So we've kind of got one example already of what a mathematical theory of consciousness looked like. And I developed my own sort of thing about measuring it based on liveness with Alexander a while ago, which I'm not going to bother going into here. So IIT is popular, right? There's been a sort of explosion of consciousness in the last 5 or so years. And I like it a lot because it has the right form of a scientific theory of consciousness. Okay, it looks like I think a mathematical theory of consciousness should look like, yeah, but it's got some major limitations, right? It's based on information, so you just can rule all that stuff out because information is not an objective property of a system. There used to be severe performance limitations. There are probably ways around that now. It used to be only work on 12 elements, but maybe that's improved. There's no evidence for it. People like it because they like the idea of mathematical theory of consciousness, not because it's true, yeah? So really it's just a wild guess, yeah? And probably much better wild guesses can be made. And it only goes one way, yeah? So I told you about, you know, we want to go from conscious states to physical states to conscious states. Tononi's theory will only go one way unless they've worked out an inverse by now, yeah? So my own view is that, you know, we've also got to do a lot of preliminary work to get the descriptions right, and actually to get all that working it's extremely non-trivial. But once we've got these descriptions of consciousness and descriptions of the physical world, then we need to kind of figure out the mathematical relationships between them. Yeah, so people like Tononi, they've sort of sat down, thought a great deal, and come up with this kind of mathematical theory. It's fairly simple. Yeah, you can write it in a single paper. It's not that bad. Yeah, but I think looking forward, this isn't going to work. Yeah, we've got this rather arrogant assumption that physical regularities are simple enough to be found by humans. Yeah, but my hunch is that that's not going to be true at all in the future. And this guy, empiricism, subjectivity, what's the guy's name? Humphreys, I think his name is. So he makes this point as well rather nicely. Yeah, so he kind of says, well, you know, we've kind of mined all the simple theories now, right? We've done Newton, we've done Einstein, even that was a bit tricky. We've done quantum theory, but the human brain's limited. We've got limited working memory. You know, we're really not that smart, yeah? So probably when we're talking about the relationship between, let's say, hundreds of thousands of neurons finding complex patterns and very complex states changing every 200 milliseconds, I don't reckon the human brain's smart enough to be able to identify those regularities, yeah? So my own point of interest in this area is to use kind of AI and machine learning to discover these mathematical relationships between consciousness and the physical world, yeah? So that's my bet on, you know, what's actually going to work here, yeah? There's a lot of sort of fairly interesting work on computational scientific discovery. They're kind of trying to rediscover using machine learning techniques like Newton's laws and this kind of stuff. And so, you know, scaled up a bit, you can imagine a version of that that can maybe identify, you know, let's say 1,000 differential equations that link consciousness and the physical world, for example. We can look at bits of them, we can see that it makes sense, but we're not going to be able to like come up with that ourselves or grasp that ourselves, yeah? So once we've managed to figure this out by whatever way, you know, we manage, then we can actually then generate predictions about consciousness. So for example, we can take a brain, we can make a measurement of that brain, we can generate a description of that brain. We can then use a theory of consciousness to generate a description of that consciousness associated with this brain. Then we can obviously measure the brain's consciousness using a report about consciousness, and we can check to see if our theories are correct. That's what I mean by prediction about consciousness, when we can actually make a prediction and check it against the facts, so to speak, yeah? But another application of this is we have a lot of systems whose consciousness can't be directly measured, yeah? So we might have a robot that might be conscious, might not, but maybe it hasn't got the right actuators, maybe it doesn't have language, but it might still be conscious, yeah? Or we might have infants who can't make reports about the consciousness, who know if it's conscious or not, or whether certain animals are conscious or not. We just don't know. Yeah. And so in this case, we can make what I call a deduction, right? We can take our system, in this case, an artificial system or a robot, but it could be an infant. We measure the state of that system, convert that into description, and then we can pump that through our mathematical theory of consciousness. So Tonini would do this, but as I said, there's issues with that. And then we can generate a description of the artificial system's conscious state. I'm going to come back to this in a bit. So once we've got this theory tested on humans, we believe it's reliable and so on and so forth, then it's got this kind of application of being able to know to some extent whether robots, infants, and so on and so forth have consciousness or not. Yeah, so it gives us an answer to how we can actually measure consciousness. Okay, so that's the story about consciousness and how we can scientifically study, if you like. Yeah, and now I just want to take a sort of bit, not quite a diversion. I know I'm running out of time, but I think I've got just about enough time. Take a little diversion through machine consciousness. Yeah, because this area is very not very popular, but it's popular in fiction, at least if you watch Netflix. But it's often confused because people are pursuing different goals within this area, and often these goals get mixed up with each other. Yeah. So I've kind of got this classification system about ways of understanding different work in machine consciousness that I've kind of figure makes kind of a fair amount of sense. Yeah. So MC1 is machines are the same external behavior as conscious humans, and actually I just work through the examples. That's probably easier. So when we're conscious, we behave in certain ways. Yeah, we have alertness, we can respond to novel situations, we can respond to verbal commands, all this kind of stuff. Yeah. And if you look at things like the Glasgow Coma scale or ways of diagnosing consciousness disorders, they're kind of using these set of criteria to know whether someone's conscious or not, because these are typical characteristic conscious behaviors. Yeah. And so MC1 consciousness is about reproducing conscious behaviors. Yeah. So if we're behaving like, if a machine is behaving like a conscious human, then they're an MC1 machine. Yeah. So to give an example, we got, Watson. So Brad and Ken can only play Jeopardy when they're conscious. It's one of their conscious human behaviors. And so Watson is an MC1 machine because it's imitating the behaviors that Brad and Ken are exhibiting when they're conscious, in a very, very narrow sense, of course. Yeah. Then there's been quite a bit of work on computer models of the correlates of consciousness. Yeah, so you might have maybe the cognitive correlates of consciousness, you don't really believe in those, or you might have the neural correlates of consciousness, for example, as well. Yeah, so it's easier with examples, I think. So this guy used to be my student, but now he's gone off and doing great things by himself. Yeah, but when I was working with him, he built this kind of neurobot system. It was like a model of the kind of global workspace, and this model of the global workspace. So the global workspace thought to be a cognitive correlate of consciousness. Been a lot of work on global workspace theory and machine consciousness, but it's also possibly a neural correlate of consciousness. So he kind of built this using neural architecture and spiking neurons. Yeah, and this is controlling the kind of Unreal Tournament video game avatar. And then there was this competition called the Bot Prize competition, where you had to, it's like a Turing test for video game avatars. Yeah, so they had judges who decided whether the avatar was being controlled by a human or by a bot. And then, we came second. We should have come first, but we had some server issues, so we didn't manage to win that one. But we did all right. Yeah, and we also linked it up with kind of Turing testing out of some kind of measure of its humanness. Yeah. So this is a model of, this is an MC2 machine because it's implementing a model of the neural correlates of consciousness, making no claims about its consciousness, just that it's modeling something that's thought to be linked to consciousness in humans as part of kind of research in this area. Yeah. And then we got MC3 machines. So obviously there's a lot of work in terms of describing the structure of consciousness. Consciousness has certain structures, it behaves in certain ways under certain conditions. Searle, Merleau-Ponty, all these people describing the structure of consciousness from a first-person perspective. Yeah, and people have also tried to model how like imagination works, for example, or how let's say, well, dreaming, there's been models of dreaming, but also people have used, let's just pick an example, Chitterabot, for example, has a sort of internal model that sort of is analogous to human consciousness. It's just a model, right? It's not pretending to be conscious, but it's a model that's a bit like consciousness. And this model here is on the right. And then this model is then fed by sensor data from the real physical robot on the left. And it's updated in response to sensor data. And it's using that model to kind of predict and plan what it should do next. Yeah? So it's kind of analogous to the way human consciousness is kind of model of the world connected with sensor data of the world and being used to kind of plan, imagine, and so on and so forth. Yeah? That's an MC3 machine. An MC4 machine are systems that really, really conscious in the way we're conscious. Yeah, so we have our bubbles of experience, and then we have a conscious machine that's kind of having smells, tastes, or whatever robots have in a spatially distributed way, if that's what they have. Yeah, there are obviously lots of different forms. So this is the kind of consciousness often talked about in fiction. Yeah, we got Ex Machina, Chappie, endless stuff on kind of Netflix, right? And then interestingly, this kind of ties up very much with the kind of transfer and uploading debate. Yeah. So if you want to upload your consciousness into the cloud, let's say, then you better make sure that that cloud is MC4 conscious, right? It needs to be your consciousness, if you say you scanned your brain and built a complicated brain simulation that worked just like your brain, that's great. It'll behave like your brain. It'd be like an MC1 machine. It'd be like an MC3 machine, it's 2 machines, sorry, but it'll only be associated with a state of consciousness if you get the physical way in which you implement it correct. Yeah. So if you want to upload yourself, you better take close attention to work on MC4 consciousness. Yeah. And so what we need to do, obviously, we need to take our artificial system, we measure the state of that artificial system, and then we use our theory of consciousness to make a prediction about whether it's conscious or not. So if we got my brain simulation running in the cloud, I need to be able to use a reliable mathematical theory of consciousness to make a prediction about whether it's conscious or not. Yeah. And we can go in reverse. Yeah. Suppose I wanted to just build my consciousness. I don't care how I build it. Then I can describe my consciousness here in XML, whatever. Then we can pump it through our mathematical theory, and then we can produce a description of the system that we need to build in order for my consciousness to actually occur when it runs. Yeah. So we can work in both ways, but we need the mathematical theory of consciousness to do that. Yeah. Skip the questions because we're running out of time. So I'm going to make a few ad hoc remarks. I will finish soon, like 5 minutes or so. Yeah. A few ad hoc remarks and some slightly less ad hoc remarks in the area of machine consciousness. Yeah. So the crucial thing to get clear here, I'm going to rearrange myself a bit, is that intelligence is a functional property. Yeah. So the amount of payoff, predictive intelligence in a system is independent of the way in which that system's built. Yeah. So there's a lot of discussion in the case of consciousness about how, how could the economy of Bolivia be conscious? How could a giant lookup table be conscious? But in the case of intelligence, it really doesn't matter. Yeah. You're either making the predictions and they're accurate or you're not. Yeah. Purely functional. Yeah. That's what we care about. The consciousness, I haven't had time to argue properly, but take my word for it. Yeah, is linked to physical properties. Yeah, it's spatiotemporal physical patterns, whether they're electromagnetic waves or neurons or whatever. Yeah, so that's why we have the problem of other minds, right? The problem of zombies. Because two people could exhibit identical external behavior but have very different internal consciousness. Yeah. So if we try to understand the relationship between intelligence and yeah, can you see what's going on behind this Zoomy thing? Intelligence and neurocortex consciousness. Okay, yeah. So as I said, there's a lot of work on the neurocortex consciousness, like global workspace implementations in neurons, all this kind of stuff. There's probably some overlap, right? Because things like global workspaces are linked to intelligence and all the rest of it. That's only just a theory. It may or may not be true. But obviously, in terms of the predictive brain hypothesis, we have lots and lots of prediction going all kind of levels of the brain, and we might be conscious of what I'm going to eat next Tuesday for lunch at the same time as I'm driving a car, for example. And while I'm driving the car, I'm doing all kinds of complex predictions that are non-conscious. Yeah. So there's only ever going to be a partial alignment between prediction, the predictive parts of the brain, and the neurocortex of consciousness. Yeah. Let's just get back to that. Yeah, there we go. So here we get kind of cognitive cortex of consciousness. So again, I don't really believe in them, but just a nod to the work that's been done in this area. So for example, Alexander Dummel had these kind of axioms for consciousness, right? So depiction, imagination, attention, planning, and emotion, for example. And obviously, these kinds of functions that they think are linked to consciousness are obviously linked to intelligence to some extent. We need imagination, do IQ tests, and do Raven's matrices and all the rest of it. Yeah. So again, there's partial overlap, but probably not complete overlap. Yeah. So the global workspace I kind of mentioned, right? So global workspace theory is actually quite a global workspace is quite a good way to build AI systems, particularly want them to think more in human-like ways. So if that's a correct theory of consciousness, which may or may not be, it may be a good description of the neurocortex of consciousness, for example, then the brain's implementation of a global workspace is probably linked to some of its intelligence. Yeah. So again, partial overlap. Yeah. And then we got stuff like higher order thought, information integration theory. Again, we could do a bit of hand waving and say, well, if brains can integrate more information, then they're probably going to be better at making predictions because compression and prediction have got quite close alignments, right? So, we can make some sort of slightly hand waving remarks about those kind of relationships. Yeah, I'm not going to go into the details. Yeah. And even a level of phenomenology, if we can see from a phenomenological first person perspective, I might say, well, I've got this really rich state of consciousness. So I've got obviously I'm aware of lots of things simultaneously, and then that enables me to make more predictions and better reasoning based because I've got more data to do it with. Yeah, if I've got really simple, small, reduced consciousness, then sure I could do all that stuff unconsciously, but there is a sort of one-way link between having a very rich consciousness and probably quite a rich intelligence. Yeah. And we also use the intensity of conscious content to label kind of online, offline states, right? So again, maybe if we've got that ability, we've got greater potential for intelligence, yeah? But there's kind of a dissociation as well, right? We can have a rich state of consciousness, but absolutely no intelligent behavior. I could just be sort of sitting there, without just absorbing the world, but just having like massive sensory system or something like that, yeah? Or we could have a system that's barely connected to the world at all, that can only be conscious of a one or a naught. But with one and naught, obviously, we could write the entire works of Shakespeare. Yeah, so you could be super smart without having any consciousness at all. So there's obviously a potential, there's contingent overlaps probably in natural systems between AI and consciousness. Yeah. Okay, so let's not worry about that. So I say it's kind of weak speculation, really, is what I'm offering you here. Yeah, because really the kind of thrust of this talk is that the overlap between intelligence and consciousness is an empirical question. Yeah, that's why I've gone to all this trouble to explain. Well, how can we measure intelligence? Well, we've got this payoff thing I've offered, but there are other ways. And then I've shown you the path to measuring consciousness, right? And once we can do those two things, we can actually have a proper answer to the question, right? We can study natural artificial systems and see what the actual relationships are in those particular systems, yeah? We can say a little bit more, and sort of vaguely wrapping up here, between the relationships between artificial systems, artificial intelligence, and artificial consciousness. Yeah, it's because we've got these kind of different ways of thinking about artificial consciousness. Yeah. So, for example, Mc1 consciousness, right? We've got lots of external behaviors linked to consciousness, are also linked to intelligence. And intuitively, as humans, if we see a system behaving like a conscious human, we're going to attribute intelligence to it. Yeah. And obviously a lot of the stuff, so when I'm asleep or in a state of epileptic automatism, for example, there's very limited stuff I can do. I'm not very smart at all, right? Most of my intelligence comes when I'm actually operating consciousness, yeah? So there's probably a close relationship between building machines that imitate conscious human behaviors and building machines that are actually highly intelligent at the same time, yeah? As machines mimic more human behaviors, they're going to be more conscious and more intelligent. But obviously there's a potential disconnect. So there's probably a big overlap in some kinds of systems, but obviously artificial intelligence can be completely different from natural intelligence, right? The kind of smarts that are going to protein folding are very different from interacting with the natural world that we do when we're conscious, kind of thing, yeah? So highly intelligent machines might not exhibit any human behavior. So we would expect there to be a dissociation between these two things in a large number of systems, particularly ones especially built to do things that humans don't do consciously. Yeah, so I can't predict protein folding consciously or play Go. I have no idea to play Go. Yeah, so I can't play that. Well, it's not pick Go. Let's pick something like some kind of high dimensional clustering or classification or something like that. I can't do that consciously. But the machine can do it. Yeah, so there's a disconnect there as well. Yeah. So there's a lot of work using these MC2 and MC3 machine consciousness. We're using models of the correlates of consciousness. We're using models of consciousness to produce more intelligent machines, right? So again, there's the work in machine consciousness is directed towards producing machines that can do more smart behavior in the world. So if we've got smart machines that think like humans, maybe we're going to use global workspace theory for that, yeah? But these are just two ways of building intelligent machines, right? Obviously, we've got self-driving cars that aren't using MC2 or MC3 approaches, yeah? Deep neural networks, again, they're not really models of the correlates of consciousness at all. So again, we expect some kind of contingent overlap, but not like particularly strong, yeah. And then we come to MC4 consciousness. It's really open, yeah. The consciousness is linked to physical properties. Intelligence is a functional property. We really have no clue whatsoever about the consciousness associated with different artificial systems at the moment, yeah. They might have conscious states as rich and vivid as our own, or maybe consciousness is only linked to certain patterns of electromagnetic waves that we don't get in artificial systems at all. Yeah, we just don't know. Yeah, and that's why again we need to measure intelligence in artificial systems, measure consciousness in artificial systems, and study the relationships between these sets of measurements. Yeah, so it's a boring conclusion, but that's where we're at. Yeah, okay, so that's this kind of thing. Yeah, okay, let's wrap this up because I know I've kind of gone on for a while. Yeah, I'm losing my voice a little bit. So I've made the case for a link between intelligence and prediction. I've given these 4 hypotheses about the relationship between prediction and intelligence. I'm kind of compelled by this, and I'm kind of working on this at the moment, and I like this, but feel free to chip in with criticisms. I'd be more than happy to hear them. Yeah. So I've got this algorithm based on these hypotheses, and it works very nicely on this agent in the maze and deep network. And I think, if we can develop good ways of estimating it in natural systems, then we can really do some nice cross comparisons between human intelligence, AI intelligence, and animal intelligence. Yeah, that's kind of where we're going with this. Yeah. Consciousness is defined as a bubble experience. We've got these assumptions that enable us to measure consciousness, measure the physical world, and look for these mathematical relationships between these sets of measurements, and I've offered this way of understanding the working machine consciousness in terms of this MC1 to MC4 framework. Yeah? So that's the sort of set of assumptions I covered. It's the sort of the core of how we need to think about the science of consciousness in terms of this relationship between these two sets of very precise descriptions. And then I've given you these sort of 4 types of machine consciousness. Yeah. And then it was kind of this boring conclusion, right? You know, that really we can sit in an armchair and make some weak inferences about these relationships, but who cares really? Because what we really need to do is do the science, and doing the science means measuring intelligence, measuring consciousness, and looking for the relationship between sets of measurements. Yeah. So if you're interested in this, there's an early version of Payoff in this Journal of Artificial Intelligence Consciousness. I'm currently working on this book chapter. Hopefully I'll be able to put an author version on my website soon, which will actually do a much better job. This is like version 1.0, and now I've kind of gone beyond that in various ways, and I think it's a little bit better, but the basic framework's all there, and the sort of rough idea behind the maths is kind of there as well. The website's there as well, so if you're interested in any of this, you've got the source code. I'll put some, there's papers up there. I'll probably put up some more papers, actually. It looks like most of the papers are missing from that screenshot. And then you've got if you want to play around with the agent maze and see how that changes the crystallized and fluid intelligence, or play around with the machine learning experiments, you're welcome to. All the theory on consciousness has gone through in a great deal more detail in my book, Human and Machine Consciousness, which you can read for free. There's a link there. And if you're interested in this area, I'm sort of, I think, executive editor. It's Antonio Cello, who did that Chicho Robot stuff. He's like the main guy, sort of one of the editors. So, I'm involved in this journal. And, this is obviously trying to explore these kind of relationships. So it comes out of the old International Journal of Machine Consciousness, and it kind of got rebooted in a slightly more modern format here. So it's kind of for mostly machine consciousness, but also exploring the relationship between machine consciousness and artificial intelligence. Yeah, there's references there. There's my website. And yeah, I'm sort of happy to take questions, actually. Hopefully, I'm sorry, went a little bit over, but hopefully it was all right. Yeah.
Very good, David. Thank you very much. Let me put here myself also as a spotlight, and my colleague Marcos as well. Very good. Very enticing and difficult topic. I have a few questions myself, but I will start with one question by Marcos here. So Marcos has this question: we humans have intelligence, consciousness, and intuition, like emotions. How would intuition, emotion be modeled, and which is the relation to the functional outcome of prediction? Okay,
so I kind of like Damasio, yeah? Do you know Damasio, Marcus? Like Descartes' error?
No.
Okay, so that's, he's been a big influence in my thinking about emotion, yeah? So for Damasio, when you perceive the world, then you have certain kind of emotional reactions to the world, right? So when I see, a tiger leaping at my throat, I feel fear, or I see, these kind of dramatic examples, but, and those reactions, I mean, in the simplest case are, produced by the brain, the amygdala, whatever, in response to certain situations in the world. Yeah, and obviously there are much milder forms of those. And so what he calls these are somatic markers, yeah? They're like markers that we apply to different states of the world in order to tag them, if you like, as good or bad. Yeah. Okay. So Damasio has a more complicated theory of consciousness, we probably don't really buy. But in terms of so in terms of our own consciousness and emotion, my own take would be, well, our emotions are consciously perceived bodily reactions to certain stimuli in the world, if you like. Yeah. If that makes a bit of sense. Yeah. So I perceive my body's states of fear that's produced by my brain in response to a certain stimulus. Yeah, and that might be hardwired, it might be low,
but how would you explain maybe that I have a wife or a girlfriend which is in Europe now, and I'm thinking of her, and I having emotions only thinking of what we have experienced or whatsoever. I mean, I'm not seeing her. I'm not having any contact with her. I'm just thinking, and actually I'm also kind of predicting or reasoning about this. How emotion fits into your model of consciousness and intelligence, basically.
All right. So in terms of so in terms of the consciousness, right? I just say it's part of this whole bubble of experience, right? We're perceiving our internal states, and our bubble of experience, right, can be driven by external data, right? In the case where I'm walking around and seeing stuff, but it can also be like internally generated, right? So when we're having imagination or dreams and stuff.
I see.
And then the same goes, right? You're thinking of your girlfriend, and then that's producing a bodily reaction of some kind. Might be a simulated one or a real one, and then you're perceiving that bit of your body as your emotion, and that's part of your conscious experiences. Yeah? Does that make some kind of sense? Yeah.
Yeah. That makes sense. Yeah. I mean, what you're saying is that we are sensing not only the world, we're sensing our body also in some sense.
Absolutely. Yeah. And some states of that body are emotional states. Yeah.
Yeah. Sure. Okay.
At least with Damasio's picture, which I find quite convincing.
I see. Okay.
And then when it comes to the other aspect which you asked about, which is to do with prediction and emotion, right? So we have this whole idea of emotional intelligence, right?
Yeah.
So and emotional intelligence, again, if you go with sort of Gardner or a lot of people who think into that, they'll sort of see it as a sort of different type of intelligence, right? But within my own sort of view of things, our ability to predict and reason about emotions is kind of similar to the ability to predict and reason about other things, but it's just operating within the area of emotions. Yeah. So, for example, I don't want to go into your girlfriend, pick someone else, right? Maybe my son, yeah. But when I see him in a certain situation, if I'm emotionally intelligent, I can predict how his emotions will be reacting to those particular stimuli because I know him well, yeah. And also, if I'm good about reasoning about myself, then I'll know that if I go into certain situations, like I've been a bit irritable lately, for example, then I can kind of predict that I'm going to behave in that way. And then if I'm good at, then I can also perhaps learn to control my emotion reactions because I can kind of predict them, right? And that's the whole sort of vague sort of field of kind of emotional intelligence, I would say. Yeah. Okay.
Yeah. I'm sorry, I'm taking too much time. I mean, there are some people which are socially very intelligent in the sense that they understand what other people need at this point and what they expect, and they do exactly this what the other person expects in order to have some boundary to them and so on. And this is also kind of a prediction. I mean, you're kind of predicting what the other person wants or needs or expects.
Yeah, exactly. So that's exactly part of that whole predictive.
Yeah. Okay, thank you.
Very good.
Yeah,
thank you, Marcus. David, I have one question here. I think that we have about 10 minutes for question. Is it okay for you if we finish in 10? Yeah. So according to the definition of intelligence that you gave us, we need to consider this setup. We need to consider each different scenario. And it's very difficult for us to go from one scenario to the other. I mean, measuring intelligence in playing Go would be very different from measuring intelligence in predicting time series for a particular, like a stock market or something. So what's your feeling about a unified theory to measure intelligence? I mean, some people would argue that we will only measure true intelligence when we go from system A to B to C and to D, and the intelligence would be the same measure. So I can understand that by now it's okay and it's needed to measure according to these division of scenarios. But what's your feeling about how far are we from a universal measure of intelligence, independent of the problem, independent of the setup?
Okay, so I don't think that makes sense. Yeah, I know that's been kind of a goal, and Leg and Hutter have this, idea of goals and rewards, and Hernando Sarario try to hack that so badly that it kind of scarcely exists. When they actually try to make it viable. Yeah, but I think when people sort of try to extrapolate from kind of human intelligence, but when you think about the potential complexity of environments that we could stand no hope whatsoever of performing in, right? I mean, the limit is, all the wave particles in the entire universe, right? And then some, yeah. So it's a failed goal, right? I think we can have a universal measure of intelligence, but we just have to relativize that to sets of environments. That's my own take on it. Yeah? And then it's still the same thing, right? We've got fluid crystallized intelligence. It does everything we want because we can still compare, human intelligence within those sets of environments to artificial intelligence within those sets of environments. We can compare AIs with each other. We can evolve AIs to become more smart. We can do everything we need to, but we're just not trying to tie ourselves to this absolutely impossible goal of trying to be intelligent everywhere possible. When in fact, you know, finite human beings are never going to get even close to that, and finite AI is even less so. Yeah. So my own view is that's never going to happen, and it's unrealistic to even hope to even care about that, I guess. Yeah.
So my next question then is playing the devil's advocate role.
Yeah.
So do you believe we were gonna achieve the singularity someday? I mean, in the next 50 years or in the next 200 years?
Okay, so the singularity as well. I mean, okay, so there's so I mean, Bostrom's a lunatic, right? I hope he's not here, but he's a lunatic. But setting that aside, I mean, it's computronium, whatever it is, right? But setting that aside, I mean, okay, so firstly, the singularity is kind of a little bit of a philosophical bogeyman, right? Because whenever people the people who are working in, you know, AI, black boxing, white boxing, all this kind of stuff, and, you know, this singularity and preventing singularity, they kind of create this sort of fictional AI, and then they sort of attribute all these properties to it so that it becomes pretty much impossible for the AI to be contained or to ever escape and all this kind of thing, right? So it makes a good story, but it's pretty unconvincing, really, yeah? And also, if you buy that intelligence is relative to sets of environments, right, which you may not buy, then I think it's perfectly feasible to develop an AI that develops very high levels of intelligence by itself within sets of environments, right? That seems doable to me, yeah. So, for example, so if we've got a sufficiently complex, you know, system, because obviously there's a limit to, if we're trying to make predictions about a very complex environment, we can't start off with a neural network with 2 neurons, right? We need to have a system that's capable of expanding itself somehow, either in terms of adding neurons to itself, whatever it is. And then we've got a realistic sort of test environment running fast enough. And that was the whole point I was making about using a measure of intelligence as a feedback signal, right? So if we imagine we're using genetic algorithms to keep it simple, yeah? And then we select the next set of algorithms, and suppose we even use genetic programming, right? We have a because this is kind of more realistic, right? We've got these programs, yeah? And we're using genetic programming to generate these programs. And then we evaluate at a certain point all of these different programs using my measure of intelligence, for example. And then we select and crossbreed the ones that are actually performing the best, right? According to the measure of predictive intelligence. And then we crossbreed and select and crossbreed and select. We plausibly, right? Without too much, you know, we can imagine we can have programs that make absolutely brilliant predictions within that particular environment we develop. Yeah? So that's a kind of singularity within, you know, a particular space or particular set of
singularity in a context.
In a context, exactly.
Yes.
Yeah? And so in the dream, right, the context would be the same as the human context, right? But that's obviously way, way harder, right? Because we can't just use genetic algorithms, because you've got kind of bodies, and robots are nightmares to work with anyway, right? But maybe within sort of more limited human environments, you know, possibly even social media or something like that, maybe you could figure out ways of expanding intelligence in those areas. Yeah. So that's why I'm being a bit whimsical, and I don't really care. I don't think anyone's going to come back from the future to kill me anytime soon, or my student for that matter, because, you know, it's always going to be kind of limited, because we're always working with sets of environments when we can produce that. But I think the thing that's not going to happen, mainly because I've got no clue how to do it, is for us to design a system that can itself design a more intelligent system. No one, as far as I'm aware, has ever even tried to do that properly. Yeah,
I agree with
you.
So
the other way they talk about the singularity is brain scanning. Yeah, and so Chalmers talks about, well, if we could run a brain like 100 times faster than a human, then that would be in itself a kind of superhuman intelligence, right? Because like Nicolas Cage, right, we could kind of think much faster and make much more accurate predictions on a shorter time scale than the average human, right? And brain scanning isn't going badly, right? I looked into this 8 years ago, something like that. We can pretty much, I think with light microscopes, we can get all the neurons, but then we obviously can't get the connections. We need electron microscopes to get connections, and people working on, you know, automating that with electron microscopy, but that's probably quite some way off before we even get the neurons and connections. And then it's not just that, right? As you know, right, there's kind of different chemicals in the different synapses. Yeah. We haven't got that data. And even then, even if we had this amazing neural model at the level of, you know, Mc1, right, you know, these kind of, you know, with all the structure and blah, 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 if we just set it running, it would probably just be a dead brain, right? We'd have to figure out how to actually get it working. And that's a whole ton of work. Yeah, so I'm not very scared about brains running faster than real time and outthinking us that. But this measure intelligence thing has wings, I think, and I'll be able to tell you in 6 months how far the student got, you know, trying to build a super intelligent machine.
Very nice. Are you familiar with the work of I think it's Marcello Maximini in Italy. He's scanning the brain with, I think, 100 electrodes, and he measures the response, electrical response of each of these spots. And then in the end, he comes up with like a summation of the activity. And he uses that for identifying if a person in a coma is really conscious.
Oh yeah, I do know him, actually. Yeah. So I've actually got his data lying around, but I haven't got around to using it yet. Yeah, he's done some very nice work because he has pre-operative epilepsy patients, right?
Yep.
So you've got your like much higher resolution EEG data from the blunted electrodes. Yeah. So he's done some nice work on the neurocortex consciousness, and I knew someone who was.
I read his work recently, and it's very nice because he produces like a range from 0 to 10. And in 3, below 3 is a person that's unconscious, and after 3, above 3 is a person with some kind of consciousness. And this connects me to the next question, which is from my feeling. I'm not an expert in conscience. My feeling is that consciousness is the notion of the self. So you have the notion of the things that you are in the world, and you are doing, and you are feeling something. That said, for me, it's much more difficult to measure consciousness than intelligence, because intelligence, as you said, is about prediction. If you can come up with a measure for prediction, you can predict like 1 second ahead or 2 minutes, then perhaps you can come up with a measure as you propose. It's a very nice way of measuring that. But what's your feeling about measuring consciousness? Because I know that I'm conscious, and I'm talking to you, I'm here now, but I will only take your word for it, because I don't know if you are really conscious or my colleague is really conscious. So how do you feel, what's your definition on this? How do you feel about having a measure for consciousness? Because for me, it's much more difficult.
Yeah, well so kind of my own sort of way of thinking about that is we need to find out a way of measuring someone's consciousness, right? And then, as you say, exactly, you've got the problem of, are you conscious or not, and all this kind of other minds and color inversion. There's all these kind of philosophical problems associated with that. Yeah, so you're not going to solve most of those problems, and that's why I've sort of proposed that we need to sort of make certain assumptions that enable us to connect the sound vibrations, if you like, if it's an audio, if it's a verbal report, with your consciousness somehow. Yeah. And so if we make certain assumptions about supervenience, which is like, the same physical body, same consciousness, we make certain assumptions about the correlates of consciousness driving the verbal reports and a few others. Yeah. I mean, if you can flick through my book, which has all these definition assumptions in there. Yeah. Then we can, in certain cases, non-controversial cases, then we're probably willing to assume that what you say about your consciousness is actually corresponds to what you're experiencing. Yeah. Right. And then we got the whole problem of untangling natural language. So so that's not going to work. So then you can imagine highly constrained situations like experimental psychology, where you show someone a red square in some corner of the visual field, and then you can kind of, in that very simple thing where your consciousness is very reduced, maybe you can kind of describe it, and we believe that what you say when you're conscious of it, that you are actually conscious of it. Yeah. So that gets us to the stage of measuring consciousness on humans. Yeah. And then we can so on humans, we can then, if we can measure the consciousness and describe it somehow, which is, as is mentioned, is a big problem in itself. And then let's assume that we can stick a load of electrodes in your brain, or we've got optogenetics, even better than electrodes, right? And so we can, measure the kind of complex patterns that are going on when you're having that particular state of consciousness. Yeah. So then we've got the data we need, if we can get enough of it, to actually put the two things together and find out the relationship between them. Yeah. That's kind of where I'm going with this. Yeah. Does that make sense? Yeah.
Yep, makes sense. Total. I have another question here from Alexandre. He's a colleague of mine here at the Big AI. Thank you for the presentation. If we could identify, measure, and differentiate types of consciousness, probably we would have something that we could improve it, and some people with money could pay for better consciousness. So how could we prevent the usage of that from discriminating against people? Very difficult question.
No, it's a good question. So it's the classic question, right? I've actually just been listening to a book on CRISPR, yeah? So gene editing. So this kind of same question comes up, right? So, all the rich people have their beautiful designer children, and all the poor people, just get worse and poorer and more desperate, and I'm sure there's films about that, yeah. So I think the first part is correct, yeah, and I've sort of discussed this again in the book, that, yes, once we understand that relationship, then potentially we can modify our states of the brain in order to enhance or change or modify our consciousness, right? And I think, I've forgotten what the film was, there's some film where you can kind of, do that kind of stuff, right? And we do that with drugs and all the kind of rest of it anyway, yeah? So in terms of discrimination, that's kind of a little bit beyond my scope, if you like. The optimist would have the trickle down theory, right? If we develop cheap ways of modifying rich people's consciousnesses, then eventually that'll trickle down, and that people with less money will be able to change and modify their consciousness, right? And by the way, I mean, consciousness doesn't actually change any of this, right? I mean, because the easiest way to change your consciousness is to change your physical environment, right? If I want to experience, a super yacht, right? And I'm, Jeff Bezos, right? I just buy the super yacht, right? And my consciousness is filled with the pleasure of looking at that super yacht. And the poor people already have their impoverished consciousnesses without that super yacht, right? So if you've got the money, you can transform your environment, which then transforms your sensory data, which then transforms your consciousness, yeah? So the direct transformation of the consciousness, in a way, is probably cheaper than buying the super yacht, right? So you can be an optimist and say, well, maybe the poor people will be able to experience a super yacht without being able to afford it. Just as we watch a film about a super yacht and we get something out of it, but not the same as Jeff Bezos or gets when he goes into space, for example. Pick another example, yeah.
Okay, very good. And this is somehow related to that series that you mentioned here, Carbon Altered, in which people have money, they can pay for more and more updated intelligence and devices.
Related to what? Say that again. So
I was just saying that the explanation that you just gave is related to that series that you showed here, Carbon Altered.
Oh yeah, exactly.
In which you have money, so you can buy better pieces.
Yeah, you get a good sleeve, right?
Yeah, exactly.
So,
would you like to go ahead and with your next question?
Okay, is that Marcus's question? Yeah.
Yeah, Marcus.
Yes, mine. Yeah.
It's about
language.
Language is a very powerful tool for intelligence, and how the complexity of language could also be a measure of intelligence, at least for human.
Okay, I haven't thought about
question
specifically here, Marcus. How do you relate language with?
I mean, could at least for humans now, or animals also, because we know that some higher animals have some kind of signals. Let's say dolphins have and whales have, so they communicate in some way. How can we say that the complexity of the language, and our language is luckily very complex, and so we can formulate many things and understand the world better because of the language? Could we use maybe language also as a kind of or the complexity of language to say, oh, this species is more intelligent than the other?
Probably is my guess. I haven't thought about it yet, but I think a lot of the aren't the kind of the language translation tools, and also in phones, aren't they based on regularities? I think, yeah, they're like they don't actually understand the language, but there's like statistical regularities amongst certain word patterns, right? And so that's kind of a predictive thing in a way, right? If you're identifying that certain words follow other ones at a very sort of simple level, there's a whole lot of regularities that we as humans are very good at manipulating, because we kind of can predict word sequences and all the rest, and we can also predict to some extent what other people are saying. So that's the sort of machine level non-understanding language, right? But then obviously when it comes to maybe, I guess even in a conversation, right? I mean, half the time we're kind of modeling what the other person's saying and predicting what they're going to say, as well as predicting what, so in a conversation. And then when it comes to species, I don't know enough about language in animals. It seems fairly basic in most other animals, as far as I can tell. Yes, you can get, I think you can teach chimp sign language, right, at a fairly basic level. I think it's like pointing to different icons, and I don't know how complex the grammar gets with them. And then you've got, Alex the parrot, right, who could talk to them to an extent. So probably is my guess, but it'd be certainly interesting to see if one could measure predictive intelligence from language, because that would enable you to get away from the problem of how we can measure predictive intelligence in humans, right? It'd be a good proxy. It's a good proxy in humans, but it's not a very good proxy in artificial systems because they're quite bad at language usually, yeah? Except in a sort of very crude way, yeah? Maybe GPT-3, you know, we could look at predictive intelligence in that, for example.
Yeah, but some people are discussing even GPT-3 doesn't have a clue about what it is writing about.
Yeah.
So let's see what happens with GPT-4.
Yeah, exactly. Yeah, I mean, it's surprisingly good compared to usual ordinary chatbots, actually. So, you know, again, I've got a student working on that. So it's like, you know, compared to your standard chatbot, it feels a lot smarter.
Exactly. Some people are calling GPT-3 as the artificial parrot because it's just repeating.
Fair, right? Yeah, it repeats and reformulates. You know, it's probably smarter than a parrot because parrots repeat without reformulating, but it does reformulate to a limited extent, right?
Yeah, exactly. Very
good,
guys.
Felipe, actually.
Questions?
I missed one from Felipe, actually.
Oh, yeah. Do you consider humans as the most conscious species on Earth? Well, according to our knowledge, probably yes, right? But if we ask dolphins, perhaps according to the notion of dolphins.
Well, it sort of depends, right? Because I mean, the correct answer is we don't know, right? Because without a way of measuring consciousness, we don't know. But also, as I said, there is a disconnect between, you know, intelligence and consciousness, right? So let's take elephants, right, or blue whales, right? They have massive brains, so brains associated with like this. A lot of the brains taken up with sensory processing, right?
Yeah,
and
the same with elephants.
Yeah, with elephants, the same, right? They've got these huge bodies, quite a lot of sensory stuff going on. So they've probably got much larger sensory areas than we've got, right? And so, and I think from the last review of the neurocortex consciousness I read was 2017, and maybe more recent ones. But the theory there, at least, was that it's actually some of these primary processing sensory areas, or maybe just a step up from those, that actually where the actual consciousness is associated with, rather than necessarily higher brain areas. Yeah, like visual consciousness is associated with activity in kind of visual areas. Yeah. So if you've got a blue whale, for example, or an elephant, let's say, then they've probably got more of that stuff than we have. Yeah. So in terms of pure sort of consciousness of the world, they're not conscious of Shakespeare, right? But they might have a, you know, more expanded bubble of experience just because they've got more neurons going, you know, hacking away at that sensory data, and so they've got a more expanded perception of what's going on. Yeah. So the answer is probably don't know, but perhaps. Yeah. And perhaps not.
The same feeling that I have. So, David, thank you very much. It was a very nice presentation and a live discussion. I know that you are many hours ahead of us. Thank you once again for accepting the invitation. Marcos, also thank you for the partnership, and everybody take care and have a good night of sleep. Thank you very much.
Okay. Hey, thanks for inviting me again.
Thank you. Bye-bye.
Yeah. Okay. See you later, guys. Thanks.
See you. Bye-bye.